Okay, welcome to the fifth video note set in Unit 3, where we're focusing on effects. This is part of the digital audio signal processing course. Got a couple readings for you down here. This will be for the first part of this note set, and this will be for the second. And we're talking about something called static wave shaping. And the first one, the first reading is focused mostly on using it to simulate or emulate tube amps, and the second one focuses on distortion boxes, various types of effects and so forth. So this is a very early approach to this. And so what we're going to do in the previous note set, we talked about nonlinearities in guitar amps, tube amps, and so forth, and also in distortion effects like overdrives and distortion boxes and fuzz boxes and things like that. And so we're now embarking on our study. This will go over pretty much the rest of the note sets in this unit. In fact, all of the note sets in this unit, all of the rest of the note sets in this unit are focused on various approaches to doing this. So the static wave shaping is the simplest, and it was one of the earliest ways to do it. So let's just look at the thing that we're trying to simulate here. So we're just looking at here a distortion box. This is the Boss DS1 distortion box. And again, the schematic comes from electrosmash.com. I've been encouraging you to go there. Loads of good information there on the analog circuits for doing these kinds of things. Really, really great place. So if you're interested in guitar effects, that's a good place to go to learn. Really good analyses of them. Anyway, this is the circuit diagram that they have there, and they've put boxes around the different stages. So we've got an input buffer, which does nothing more. It's unity gain, emitter follower. Its job is nothing more than to provide a reasonably good input impedance into the box. Then we've got a transistor booster, just classic common emitter amplifier with some stabilizing bias feedback there with a capacitor, bypass capacitor around it. So that's a classic circuit that you may have learned. You may have learned it with this resistor going up to the supply, but this is a variation on that to provide a little bit of DC feedback to stabilize that bias point. So I don't know, I suppose I could analyze that, and I'm sure Electrosmash did that to try to figure out how much gain is in that stage. I don't know. They call it a booster here, so I'm guessing there's probably a little bit of gain in there. But probably no real distortion occurs there other than maybe a little bit just from the inherent nature of bipolar transistors. Then we've got a unity gain op-amp stage. Again, that's probably nothing more than just providing a buffer to the driving point of that amplifier. The output impedance of that transistor booster stage is probably not super low. Then we get into the distortion here. So we've got an op-amp with an adjustable gain driving this parallel pair of anti-directional connected diodes. I don't really know what to call that structure, but I'm just going to call them parallel back-to-back, although back-to-back doesn't really fit, diodes. But that's a diode clipper, so let me just call it that, little diode clipper there, and this controls the level of the signal going into that. So if the signal going into that is kept fairly low, then very little clipping. And as you increase the gain of this stage, more and more of the tops will get clipped off by that 0.6, 0.7 volt threshold of the diodes. Then tone control. There's a power supply up here, not very interesting. but it, physically has to be there. And then an output buffer. Again, nothing more than emitter follower, mainly just to provide a nice output impedance of the box so that you can send it on to the next thing that you want your guitar to go through. And we also have a 5F2A Fender amp. So this is a 1950s Princeton Tweed amp, as they're called. So one of the first in the early lineup of the Fender amps back in the 1950s. And we see two triodes and power tube, 6V6. So distortion happens in a lot of those places. Depending on the level of the signal coming in, we'll probably get some distortion there. If it's a hot signal coming in, then we amplify it and we go through another stage of amplification. And again, there will probably be some distortion there. And then based upon how loud you have the volume set, you may or may not get some distortion in the power tubes. But the point here is what we see is stages of linear electronics and nonlinear electronics. So we see some nonlinearity here, followed by some linearity. And, for the purposes of our discussion, let's just assume that no real distortion is happening there. So we get some nonlinearity or some linearity there. With some frequency response shaping, because we've got some AC coupling that forms a high pass filter and so forth. But the big thing is a distortion followed by a filter. Okay, same kind of thing down here. We've got distortion followed by a filter. That's our tone control. And some more distortion followed by a filter. That's a high pass coming from the AC coupling of the second triode into the power tube, and so forth. So what we're seeing here is cascades of stages, linear stages, nonlinear stages. That's the idea. So if we're trying to emulate these kinds of things, we should probably be doing a similar kind of thing. Now, as we go further in this, we'll see better and better ways to go in and say, I want to emulate that stage, and I want to emulate that stage, and I want to emulate that stage. But for right now, in our studies, and this is where things were in the very early days of these, discrete time or digital modeling approaches to guitar effects and guitar amp sounds. In those early days, it was done in a very simplistic way. So that leads to this idea of static wave shaping. So we've got a linear filter and a linear filter sandwiching some sort of static nonlinearity. The static nonlinearity means this is a function whose output, whose output here depends only on the one and only one sample in. So whatever is here at a given time completely determines what is here at a given time. That's different than a linear filter, right? Remember, convolution or recursive filter, ideas of difference equations. For a linear filter, we're thinking of those as having some sort of dynamics, some sort of memory. So the output here at a given instant of time depends on the current input plus a whole bunch of past inputs, or equivalently, past inputs and past outputs. So that's the difference. That's why we call this a static nonlinearity. So this static nonlinearity needs to have some sort of shape to it. And so there can be symmetric nonlinearities and asymmetric. We'll see examples of each of those in subsequent slides. And those nonlinearities can be soft versus hard. So a soft nonlinearity just kind of smoothly bends away from a line. And the hard nonlinearity is just like hard clipping. it goes up following the nice linear line and then just gets harshly and hardly clipped over. And we'll see examples of each of those. And each of these things, each of these different characteristics will give different sounds, and we'll explore in this note set how those different effects come to be due to the symmetry or asymmetry in the soft versus hard. Now, one thing that we're doing here in our discrete time emulation or discrete time modeling is we're assuming that whatever I put in here has no effect on how this works nor on how that works, and vice versa. This has no effect on how that works. So there's no interaction between the stages. And that's not an assumption, that's just how we're going to implement it, right? We've got a MATLAB function that does this, and the output goes into this, which is a MATLAB function if we're just trying it out. Not, obviously we can't use MATLAB to implement it in real time. But those two functions, they don't change how the other one behaves and operates. So that's different than how things happen in a real analog circuit. So in a real analog circuit, each stage interacts with the next one. And we'll see that later when we get to more advanced ways of modeling amps and effects. We'll see that the stages interact, and we should try to capture that in our emulation, in our models that we use for that. But for right now, in the very simplistic view that things started off in, and in this note set, this is what we're going to view. That's why we call this a static nonlinearity. So what I'm going to do here is take you through some of the stuff that's in reference 1, a very nice review paper of some of the early approaches to nonlinearities, primarily focusing on tube amplifiers. I can't remember if they do anything on effects, but for effects, I switched to reference 2, which I think was the DAFX book. But let's go through this. And basically, they're just doing kind of a reference review, a literature review. They're going through a bunch of patents and some papers, and a lot of this early stuff was not in academic papers. It was in patents. Now, if you've never read a patent, maybe you don't know. Maybe you think that a patent is going to tell you everything there is to know about how to implement that, but that is not the case. Most patents try to convey the new idea without giving away too much so that others can't really figure it out. Unless they agree to pay royalties to the patent holder, then they might get the full-blown description. But if you read a patent, there's not going to be all the details in there. So anyway, I'll just give you some ideas based upon what's described in reference number 1 of some of these patents and so forth. And then a few of the things that we'll cover are actually in papers. So way back in 1996, I don't know if this was the very earliest one of these, but this is where this review paper started. Patent number, blah, 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 blah. You can actually Google this and you can find that online and read it if you want. This is assigned to the company Yamaha, so a big music company, as well as making lots of other things like motorcycles, for example. Same company, actually. And here's the actual people who did the inventing. And this is the year that it was, that the patent was issued. So usually takes 2 to 3 years for a patent to be issued. So this probably was submitted about 1993 or so. You can track that down and find out exactly when the submission date was. That means it was being developed maybe a year or so before that. So we're talking early 1990s is when these ideas were starting to be developed by these two inventors at the company Yamaha. So we've got a guitar, goes through, there's probably some analog electronics out in front, goes into an A to D converter. There's some scaling here. I put that in with red to call attention to it. We need to make sure that it's going in at the proper range of levels in the mathematical function that we're going to put in. But you can see that we've got, function, 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 and some of those could be distortion. And I think here they're saying that they are distortion. So we could have a cascade of 3 different distortion static nonlinearities, and then followed by linear effects. So that could be, some of the, flangers and things that we've already talked about, but that could also just be filters. And, maybe this is a linear filter, and maybe that's a linear filter. They're showing it as the same function, but I suppose you could do it as 3 different things, maybe with the distortion sandwiched in the middle. But what function did they use? So I drew a red line here that kind of approximates the center part of this blue curve. That's this fx, f of x thing. And you can see that once you get above, say, 0.4, the function starts deviating quite a lot from linearity. So if we just had the red line there, we'd be creating no distortion at all. We would just be creating a little bit of a gain, right? 0.4 in and 0.6 out. But it starts to bend over, and that's the distortion. For a sinusoid, that will start to round off the tops of the sinusoids. If you increase, so if either you change the scaling here or you increase the value, or the volume of your guitar going in, you might actually get all the way up to here where things are being clipped quite a lot. But that would be a user's adjustment. But this is the idea. And this is following the viewpoint that we just laid out on the previous slide. And what is this blue function? It's this little thing here. Where did they come up with that? No idea. Patent doesn't really say why they do that way, where they got the idea, what they're trying to mimic with it, nothing. Just here it is, we're patenting this idea. Now we can see that this is a symmetric nonlinearity because what happens on this side is a mirror image of what happens on this side. We can also see that it's an odd symmetry. We can also see that this thing is very linear in the middle. So for small input levels, you're not getting any distortion at all. And then for larger input levels, we are getting some deviation from the linearity, but it's a pretty mild nonlinearity at the extremes. Okay, so that's starting things off. Let's go just a couple years ahead, at least issued, patent submitted probably a couple years before that, and developed a couple years before that. So this could have been under development just after Yamaha's, or maybe even around the same time. Some patents take a little longer to get issued and so forth. But anyway, this is by a company called Line 6. So if you're into guitar, I'm sure you've heard of Line 6. They were one of the first and one of the biggest companies to do digital modeling of amps and effects. And this is one of the founders of the company, and I just wrote et al. That means and others. But Doidek was one of the founders, and I think maybe the main guy who started Line 6. So what do we see here? Same kind of thing. We see guitar going into an A to D converter. And these figures are from the reference 1, so that's probably why they look similar to each other. They probably redrew them from the patent. We've got some preamp effects. We've got linear effects. They show only a single function. Of course, that really could be just actually a cascade of several nonlinearities, but once you've cascaded them, it ends up just being one function. But there's your static nonlinearity. And then they actually show going into 2 possible channels, because this linear effects here might be creating a stereo signal. So you might have, some sort of ping pong delay or something that's going back and forth between channels. Now, here's the big thing, and I'll comment on this down below. Upsampling by a factor of 8. We talked about that in our previous note set. We said that nonlinearities can create aliasing, and right here in the line 6 patent, I don't know if this was their very first patent, but one of their early patents, line 6 was saying, hey, we need to increase the sampling rate by a factor of 8 before we go through our nonlinearity. Then we bring it back down so that we can do the rest. And I show filters involved, right? When we upsample, there's a filter. Remember, we studied that and we said to upsample, we stuff in zeros. So in this case, in between every real pair of samples, we'd stuff in 7 zeros. And then that, in the frequency domain, created a bunch of image spectral images, and the filter needed to get rid of those. Then we go through our DSP. It's going to create some aliasing out beyond the 20 kilohertz that we can hear. And we can't go back down to our sampling rate until our desired final sampling rate until we filter and then downsample. So this filter here happens first, and its job is to get rid of all of the stuff that would alias down into the actual audio range if we were to reduce back down to our standard sampling rate. So that's the idea. So what did this patent say to go into that function? Two different options. So one is this asymmetric one. That's this red one down here. Again, they say no idea where this came from, although in just a few slides, I'm going to give you a hint as to where I think it really came from. But they didn't say that. They didn't say that in the patent. And look, this is some crazy nonlinear thing. 12th powers, absolute values, squares, and constants done over a 3-interval piecewise definition. So down here, -1 up to almost -0.1. So -1 up to about there. This part is described by this 12th order thing. And then from there up to 0.3. So from there up to about 0.3. So this region here is described by this quadratic. And then from there on is just a constant. So that's how that's defined. And look, this is very nonlinear. This is, not even close to the straight line. And we have clipping, pure just clipping on the positive side. Not quite clipping, but some severe nonlinearities on the negative side, very asymmetric. We'll see where that came from in just a little bit. And then there's the symmetric one that they proposed. And so here is the function for that. This sign of x just takes this thing here, which is always positive, right? Absolute value in x squared, and just applies the sign of x to it. But it's going to look like this. And we see that that looks very close to the one we saw on the previous page from Yamaha. Okay, so again, they didn't say where that came from. It's different enough from what Yamaha had that they could patent this. I'm sure the patent examiners checked and made decisions as to whether this was sufficiently different. So you can check that out. But my opinion, I think that the biggest thing in this patent was this idea of upsample and filter. Well, plus this asymmetric thing, which we'll see later. But I think this may have been the first time that it was recognized that if we're going to be doing this static nonlinearity, we really need to upsample. Okay, 1998. So remember, 96 was Yamaha, the first patent that we saw by Yamaha. I don't know if it was their absolute first in this field, but it's the first one we looked at. A couple years later, coming out at the same time as the line 6. Again, I don't quite know if they were submitted at the same time. Now we've got some new ideas coming out of Yamaha. We've got EQ and tube stage, EQ and tube stage, and then a splitting and into two tube stages. And they say down here, or at least reference number 1 labeled it that way, that's modeling what's known as a push-pull power amplifier model. That's the structure in higher powered tube amplifiers. It wasn't in the Tweed Princeton that I showed you. That was what was known as a single-ended power amplifier, one power tube. But this thing is modeling that. So that's kind of cool. And then we've got, look, ... So any number of tube stages here. And we've got filter. So linear filter, nonlinearity, linear filter, nonlinearity, linear filter, nonlinearity. And there can be indefinitely many of those. You'll also notice that there's a -1 after each one of those. That's because tube stages are inverting. So they're actually even modeling that in this. Not that that's really going to make much of a difference. Okay. They also do this tube stage. Each tube stage has a static nonlinearity, but it also kind of picks off the value here and calculates a number, a sample that then is fed back to offset the signal going in. And so that's a time varying bias offset. And it just creates a more complex nonlinearity because it's time varying, and it does create it takes a symmetric nonlinearity and gives it a small amount of asymmetry. Again, the patent doesn't really say why, so it's not clear how this relates to actual tube behavior. But I think that what they're trying to do is there are some aspects of actual physical tube operation that kind of the bias is changed when the signal is applied. And maybe they're trying to capture that. They don't say, but they may just be doing it because they did it and they thought it sounded better. So again, patents don't tell you these things. Now we're into an academic paper. This is in the Journal of New Music Research, came out in 2001. Distortion of music signals by means of multiband wave shaping. So we're still in this static wave shaping kind of idea. And so here's the idea. We put the signal into a filter bank. So that's a lot like the graphic equalizer that we talked about, except we don't immediately sum the outputs of the individual bandpass filters. We take each channel's output, or each bandpass filter's output, and each one of those signals goes through a wave shaper that's going to look like this. So there is some scaling here. It's just computing the average value of the signal, and then it just divides by that average value. So whatever's coming in is X. So that's just trying to make sure that it fits nicely into the range that the mathematics is defined on. We've got two different nonlinearities operating in parallel, and then there's some sort of adjustable mix, and that mix is controlled by the value coming out of the averager. Then the average is also going back over here to scale things back up. So this multiplication kind of undoes that. So we're just scaling it to fit appropriately within the extremes, defined extremes of our nonlinearities, and then scaling it back up. So the key idea here is it's right there in the title. Break down into multiple bands. Apply a nonlinearity to each band separately. And the intent here is that we talked about how there was lots of cross nonlinearities between, if you put in multiple sinusoids, they would interact with each other. So this is trying to reduce the amount of undesirable intermodulation distortion. So that's the idea. And then this is just describing what the paper says, and also what is characterized in reference 1. what these nonlinear functions are. So unlike the ones that we saw before, which just look like weird polynomials coming out of nowhere, they propose using something called Chebyshev polynomials. They're very famous and used in a lot of different applications, and they've got some nice properties, but that's what they're proposing to use here. Why? Not quite sure. And then the two polynomials are used in parallel, like we see here. The outputs are mixed, and there's some sort of dynamic mixed level determined on by the average level of the input signal. So moving forward, and again, this idea, they're just showing, input to output, but this part here can be sandwiched in, right? We could go back to this Yamaha one. We could use that idea here and here and here and here if we wanted to. So that wouldn't invalidate the Yamaha patent because we're doing something different for the nonlinearities. So that's the idea in that paper. Now, this is an interesting paper. It's not so much talking about how to implement these digital models. It's talking about how to figure out what nonlinearities you should put in there. So again, right in the title, a measurement technique for highly nonlinear transfer functions. Doesn't say anything about tube amps, but that's what they're aiming for. And this is at a conference on digital audio effects, DAFX. That's actually the conference that gave rise to the DAFX edited book that I use for a lot of the material in this course. And so basically it outlines how to take an actual tube amp and measure the nonlinearity of the stages, but it's measuring it as a static nonlinearity. I don't know exactly how they do this, if they just take that nonlinearity out of the rest of the circuit so they don't get any of the preamps or the filtering stages on each side, but you'd have to read the paper to find that out. Now, the first thing they did was they ran a SPICE model for the amp. And yeah, so you can get SPICE models for tubes, and they're actually pretty good. So you can simulate in SPICE or LT SPICE if that's your preferred way to do it, which for most people that is. You can get these tube models for LT SPICE, and you can create the circuit diagram for, say the Vox AC30 amp or the Princeton Tweed amp, whatever you want. And you can look to see what the signals look like at each place. So they did that, and then they applied their measurement technique, and they have a very specific way of measuring these nonlinearities. And we'll talk a little bit about that later on as well, although we really already talked about that. Back in Unit 1, we talked about how to measure the impulse response as well as nonlinear impulse response components of a system. So I think it's similar along those lines, but I don't want to get into the method. I want to look at the result. So they did this first on a SPICE model, and then they did it on an actual amp, which was a Vox AC30, famous amplifier. Brian May of Queen was famous for using that amp, and I think the Beatles used those for part of their time. And they measured this, and this is a figure right from their paper. So I didn't take this out of reference 1. I took this from this paper. In fact, I don't think this is covered in reference 1. This is right out of their paper. Does that look familiar? Look at that. Look at the red curve here. That's line 6's asymmetric one. Just flip it around. So this is the reverse, and that's because of that, maybe that inversion in a stage of a tube amp, and they just didn't put the inversion here. But this part looks like this, and this part looks like this, and this part looks like that. So yeah, So guess where I think line 6 got their crazy 12th order polynomial defined thing? They probably came up with a way to measure an AC30 and they published that. Um, or they didn't publish it, they put it into their patent, but they didn't say where they got it. And if you read the early line 6 literature, the manuals that came with their products and so forth, they talk about, we've got a such and such amplifier and we put it in the lab and we measured it. I think that's what they did. So once it's been measured, then you can try to find a function that mimics it. And that's what line 6 did. They had that crazy 3-interval piecewise definition where on one of the intervals it's some crazy 12th order polynomial. Or you could just use a lookup table. So you just say, here's all my input values on some fine enough grid. You define what all the output values are. And then you just take your actual input, take two adjacent values and interpolate between them. So just probably linear interpolation is good enough to do that. There is a patent way back in 1991, so there was some earlier activity than where we started that talked about this idea of lookup tables for implementing nonlinearities in this field. So things started very early, 1991. Okay, so that was some early things for tube amps. And there were lots of other ones, but those are representative to give you the idea. You can go through the literature and find papers and patents to your heart's content. But I just presented a few representative values. Now let's turn our attention to static nonlinearities that might show up in distortion boxes. So overdrives, distortion, fuzz boxes, things like that. And I've already commented that right there is the heart of it. And here we see that there's an RC filter that kind of drives that or precedes that diode clipper. But that's the heart of the distortion sound of so many different distortion boxes or overdrives. So the DS1 just has it sitting here between the output of an op amp and a tone control, and the Ibanez tube screamer had it up in the feedback loop of an op amp. But nonetheless, it's the key to these things. Now, we might also get some extra distortion from these. The fact that they call it a booster might allude to that, but I don't think that's the main essence of the distortion in this. So we should just focus on this, and maybe that's a linear filter that we would put in front of that, and this would be a linear filter that would be after that. So hearkening back to what I showed on one of our early slides here, linear filter, nonlinearity, linear filter. So this is the tube screamer. Here we can see the diode clipper in the feedback loop, and we see some linear filtering going on there. We see some linear filtering here for our tone control. So again, linear filter, nonlinearity, linear filter, that kind of idea. So we've got a distortion and an overdrive. They both have this diode clipper in there. Now, we'll see later that we can actually mimic perfectly, quote unquote, this diode clipper. Here we're just going to say, well, it's a nonlinear function and we can choose what we want to put in there. That's the idea of a static nonlinearity. So let's look at some things, and the things we're going to look at all come from reference number 2. So I don't know if anybody actually ever used these things to simulate this, but this is the idea. So here's something called symmetrical soft clipping. So you can see that once you get up about 0.6 level of the signal, it just levels off and clips the signal. But it gets there in a very soft way, and prior to that, it's virtually linear. And so you can see that here we're just defining it for positive values, and obviously since it's symmetric, it would just be repeated for the negative values. So you can see up to 1/3, it's just linear with a gain of 2. And then from 1/3 to 2/3, it follows this quadratic. And then from 2/3 to 1, there's the clipping to 1. But this quadratic gives that soft curve into the clipping. And the way that reference 2 shows how this behaves is it puts in an exponentially decaying sinusoid of 1 kilohertz. I don't think they give much detail on what the exponential level starts at and how fast it decays. You can actually deduce that if you're clever, but it's not important. So we've got a sinusoid that's going in, and the envelope is some sort of decaying exponential. So whatever decay rate and starting value that is. And then the sinusoid is going to bounce sinusoidally between there. It's actually oscillating much faster than what I'm showing here, and it's actually sinusoidal, not triangular. So that's the thing that goes into this nonlinearity. So you can see when it starts large, it's going over this range, and it is hitting the clipping. So in the early samples of the output, you can see the tops of the sinusoid being clipped off. But you can see that there's a little bit of roundedness there. That's because of this. But then as time goes on, remember the input's amplitude is now lower. So 2,000 samples in, now maybe we're just barely getting to this little soft nonlinearity. And now we can see that instead of this flat top, we have a rounded top. But it does not look like a pure sinusoid. It's a little wider and a little rounder than a sinusoid would be. And if we went further than this, if we went further on out, you'd eventually see something coming out, and it would be a perfect sinusoid here. Because now we're operating in this perfect linear mode. So that's the idea. We can also look at this through a spectrogram or short time Fourier transform. So the DAFX book calls this the short time FFT, but remember the FFT is an algorithm. The DFT is the thing. So this is really a short time DFT. And we can see that when we start with a high level input, so this thing starts with inputs that are, with a sinusoid whose values are bouncing between plus and minus 1, we're getting a lot of distortion. And remember, distortion creates harmonics. And so here is the original 1 kilohertz sinusoid, and you can see its amplitude going down. It's a little hard to see that on the scale and with this perspective. But you can also see that in the early range, so only up to 250, so very early here, we get lots of harmonics that are pretty strong. We also see that because of the odd symmetry of this, we can work through the math, and it will tell us that we get only the odd harmonics. So if 1 kilohertz goes in, we get that fundamental, but then we get the odd harmonics, 3, 5, and 7, the odd multiples of that. But we also see that as the input exponential decay makes the sinusoid's amplitude get smaller, eventually we are getting less of a distortion. And so now around 2000 here, we can see that we're getting lower level of these different distortions. Now, some actually go up a little bit, but primarily things are decaying down along frequency faster. And then eventually when we get to the point where we're down into this perfect linear part, all of those harmonics go away. But you can see that the higher harmonics go away or at least become significantly insignificant. I like that. Significantly insignificant. Where did I come up with that? Those die out sooner than these die out, or at least become negligible sooner. But eventually you get to a point where there is nothing, no harmonics, because we're in this perfectly linear part. So what does that sound like? Don't really know, but you should be able to take an audio signal, record a guitar signal, bring it into MATLAB with the audio read command, implement this nonlinearity, and listen to what it sounds like. Now, you might want to put some filtering after that. You can play around with that. And you might want to upsample to a higher sampling rate following the line 6 idea. So upsample to a sampling rate 8x. Do your nonlinear processing, filter back down to 20 kilohertz, and decimate down to 44.1, something like that. And you could hear what this sounds like. Okay, so that was soft clipping. Now here's hard clipping. So the black curve is what we just looked at. Hard clipping just goes up linear right until 0.5 and then straight across, perfectly flat. I didn't even write out the function for that because it's pretty obvious. And so now here is the output for the exponentially decaying sinusoid of 1 kilohertz. So we can get some idea here as to the amount of clipping of that as to what level we start at with the exponential decay, exponentially decaying sinusoid going in. But you can see up until about 5,000 samples, it's just hard clipped, and then that's where it gets below this where this nonlinear part starts. So at around just before 5,000 samples, the amplitude has dropped to 0.5 or less. And so now this is just the perfect exponentially decaying sinusoid. And so here is our spectrogram. Right around where we expect, everything stops. But prior to that, things kind of stay the same. There's a little bit of fluctuation, but not too much. But again, we still have an odd symmetry, so we still get our odd harmonics of that. So this is going to sound different. It'll certainly sound different on a guitar as you play louder or softer. Its response to that will be much different than the soft clipping that we saw on the previous slide. Now here's a soft but highly nonlinear. So remember we looked at soft clipping and this was mostly linear through this region and then just suddenly got softly clipped. So instead of clipping now, we're just doing lots of nonlinearities. It's hard to find a region where I can fit a straight line, maybe just something really small. So this one is defined with a gain control. So whatever level your signal goes in, there's a gain knob that you can use to push it further out this way. So I'm plotting gain. That's not convolution, that's times. Gain times the input sample. And so now we can see that, this never really harshly clips off the top. But early on, with a large amplitude, the region where the sinusoid has a large amplitude, it's very rounded. And then later on, around 5,000 samples in, the input has gone down quite a lot. And now we see, well, if you compared that to an actual sinusoid, you'd see that there is a little bit of deviation, but not a lot. And then here's our waterfall representation of the short time Fourier transform. So frequency along here, time going along here in samples. And now we see a very, very different structure here than we saw for the previous two. So go back and take a look at those. But again, odd symmetric function gives the odd harmonics only. So that's interesting. And then our last slide here is some sort of asymmetrical, highly nonlinear function. And I just picked this out of the book. I don't know if this is really what a fuzz face does, but it's going to be along those lines. And you can see there is a control here called distortion. So that's the amount of distortion that you would get from that. So I don't think the book gives waterfalls for this. But I did find some plots of this. I don't think this is the effect of that nonlinearity, but it's the same kind of idea. So this does look very much like modeling a fuzz face, and so we can see this at low input values. We see not much nonlinearity happening, but suddenly we get very asymmetric nonlinearities, driving it to a asymmetric square wave kind of thing. And here I'm not showing the waterfall, but essentially you can get an idea of how the harmonics change. So this is just a spectrum. This is a spectra of that. This is a spectra of that, and all the way down to this is a spectra of that. A spectrum of that. But this is asymmetrical, and we get all of our harmonics. 1, 2, 3, 4, 5, ... By the way, even symmetry would give just the even multiples of the fundamentals. Those aren't typically used for distortion because we want our signal to go positive and negative. So anyway, this is a very brief look at some very early ideas for modeling distortion in guitar amps and guitar effects. This is by no means the end of it. So, you know, in the early days, people were saying things like, well, these modeling things don't really sound that good. They're good for bedroom players, but not ready for prime time. But it didn't take long before companies like Line 6 and others, I'm saying Line 6 just because that's the stuff that I've played the most, and I'm not as familiar with other companies. But companies like Line 6 and others like that soon started to really improve this. And it wasn't long before people who were in the studio were starting to use some of these ideas instead of, or some of these devices rather than dragging in actual guitar amps. And today, there's a lot of pros who are using modeling effects for guitar amps and for effects boxes. So, the rest of the note sets in this unit will proceed looking at more and more advanced ways. Now, will I take you all the way up to what's going on today? Probably not. I put this course together back in maybe 2018, 2019-ish. And I've tried to add some new things, but it's a hard field to keep up with because stuff is coming out of companies. So it's coming out as patents or not coming out at all. But we'll see some of the more advanced stuff in subsequent note sets in this unit, and I hope that you'll be able to join.